Welcome to Chapter 8. This chapter is about rational exponents and radicals, both radical expressions and equations and functions. So we're going to start with sections 8.1 and 8.2. This video is going to be broken up into parts, so please make sure you watch all the parts. As we do this, please also pace yourself because a lot of this is going to go back to some exponents that we've already dealt with. So first off, let's go to rational exponents. And as long as we're talking about exponents, let's go to exponent rules. So I want you to pause the video and I want you to think, what are all the exponent rules that you already know? Go ahead. Well, you may have referred back to chapter 5 to kind of quickly remind yourself. There are several that we have. First off, we have the product rule. That's when I add the exponents if I'm multiplying. We have the quotient rule. Subtract the exponents if we're dividing. The zero power rule. We have negative exponents. We have the power rule, power distribution, the power of fraction rules. So we have all of these. If you can't remember what any of them are, again, go back to the beginning of chapter 5. We went through all of them, and we're going to use them in this chapter. So if you struggled with them, even if it was negative exponents, you thought, oh, sweet, I'm never going to deal with them again. Well, I'm sorry, they're back again. So with all this in mind, let's also talk about what on earth are rational exponents. Well, a rational exponent is an exponent that's a rational number. Okay. What's a rational number? A rational number is a number that can be written as a fraction. So just like we deal with rational expressions in the last chapter, a rational number is any number that can be written as a fraction. There are some numbers that can't be written as fractions, but we're not going to really get into the details of those quite yet. We'll actually deal with that in this lecture. But please make sure you take the time to understand that it's a fraction. So what's that mean? Well, it means we're dealing with things that look like this. Notice I have fractions as my exponents, 2/5 and 1/5. But I want to simplify, and I'm multiplying in this case. So which rule do I use with the exponents? Hopefully you're saying, oh, it's the product rule, so I'm going to add the exponents. Okay, well, how do you add fractions? Going back to the last chapter, you add fractions by just adding the top. So that's just going to be a to the 3/5. It's that simple that we're just trying to write these things using fractional rules and exponent rules all mixed together now. So what about this one? Which rule are you going to use and how would that work with this particular exponent? So I want you to pause the video and try to do this based on your exponent rules that you know. Well, hopefully you realize this is, because I have a power inside of a power, this is the excuse me, this is the power rule. So I'm going to multiply. Well, when I multiply, I get 12 over 15, but I can reduce that fraction down to 4/5. And just like that, we have simplified our expression. All right, well, what about this one? Which rule would you use to simplify this? Try using your exponent rules, manipulating things, and remember to get a positive exponent, what we want at the end. Go ahead. Well, as a reminder, if I have division, it means I'm going to subtract my exponents. What's 1 minus 5? Because they're fractions, they have the same denominator. So just 1 minus 5. That's going to give me -4. Oh, I don't like negative exponents. So I need to change that to be 1 over x to the 4/7. So this one involved both the quotient rule and the negative exponent rule. So we're just keeping all this in mind and using it. Now what about this one? How would you multiply these together? Go ahead and pause the video and try to do it based on what we've already talked about. Well, hopefully as you approach this one, you first said, okay, I got -2 times 3, which is -6. So that takes care of the numbers. What about the x's? If I'm multiplying the x's, I add the exponents, which is going to be x is 2/3. It's subtraction because this is negative, but it's -1/4. So I can just leave it as a negative exponent because I'm now just doing subtraction. But I can't subtract them as is because they don't have the same denominator. So we got to change them. How would you change them to have the same denominator? Well, I can multiply that to 4 over 4 and then 3 by 3 over 3. If you do that, I get 8/12 minus 3/12, and that's x to the 5/12. And just like that, we're done because now we have a positive exponent. So we're happy about how we simplified it. So notice again, fraction rules over and over again are going to play a bigger and bigger role. Well, what about this one? We've talked about multiple options. I want you to try to simplify this. Go ahead and go. Well, again, this one you may have noticed is division, which means I subtract. Well, but 2 minus a negative is the same thing as 2 plus 8/3. But how am I going to add that? Because, by the way, we do not use mixed numbers in our exponents. They have to be improper fractions. So we want improper fractions. Well, I got to change that 2 to 6 over 3. And then if I add them together, I get 14/3. And that's enough. We can stay with that because that's already in simplified form. We'll talk a little bit later about a different form we can write that in and some other things we can do with it. But for now, that's all you know how to do in terms of this. We're just using the exponent rules to simplify. Well, let's now use these same exponent rules to evaluate a number. So I have 25. It seems a little bit odd, but 25, we can write that as 5 squared. Now, if I write it this way, can you now use the exponent rules to simplify that? Go ahead. Well, hopefully, as you did that, you recognized I can multiply the exponents. And 2 times 3/2 is, well, 3. So 5 to the third power is 125. It's 5 times itself 3 times. But notice the critical part about that was factoring 25 into 5 squared. Because we were able to do that, we could then use the exponent rules. Well, what about this one? How would you be able to use something similar on this one? Try it, and then unpause the video. Well, first off, we need to factor -8. And I can factor that into -2 times -2 times -2, or -2 cubed. Now, if we multiply our exponents, notice I get -2 to the -2. The duplication just happens to be the way it is. But I can't really do any calculations until I change it to a positive exponent. So I need to move that to the denominator. So it's 1 over -2 squared, which is 1/4. So all of this came back to this idea about how do we factor these numbers. That's going to play a really big role in this section, specifically in 8.1 where you're doing the problems. It's pretty much going to be squares and cubes. You maybe have 1/4. It's something to a 4th power. It's not going to be that tremendous. We are going to talk about those a little bit further. All right, let's do one last example. Kind of do all this rational exponent rules, and then we'll move on to talk about something really useful for it. But in this particular case, when I'm dealing with this, I want you to use all the exponent rules to simplify this to as positive exponents. Go ahead. Well, hopefully you've already done this. The first thing I would do is I would simplify what's inside the parentheses. So notice if I divide, that means I'm going to subtract all these exponents. Well, that's going to be -7 plus 1, and this is 3 minus 1. Or in other words, a to the -6 and b squared. Now notice, I also took 36 and I wrote it as 6 squared. I did that because that's now going to help me. I now can distribute this exponent into each of these terms. If I do that, so I'm multiplying to each term, and they all are multiples of 2, which is really nice because that turns into 6 to the -1, a to the third power, and b to the -1. Now we just take things that are negative exponents and they move down, while the a cubed, which has positive exponents, stays on the top. And just like that, we use negative exponents to get through this. Now, you might be wondering, why do I care about these rational exponents? Well, it's actually because this very next, and that's how they are tied to what are called roots and radicals. So first off, let me just hit something. 5 squared means it's 5 times 5, right? But what does 5 to the 1/2 mean? Because we know if 5 to an integer, we can just write it out that many times. We added negative exponents, it got fuzzy, and now we got fractions. What's that mean? Well, to understand that, think about it for a second. What is 5 to the 1/2 times 5 to the 1/2? Well, that means, remember, we add exponents, so it's just equal to 5 to the first power, just 5. What that means is that 5/2 is a number that multiplied by itself is just 5. So it's some number that exists that if I multiply by itself, it's 5. Similarly, what's a square root? Now this symbol here is called the square root symbol. That's that funny little, like almost like division symbol. Well, it means a number that squared is 5. But a number squared is the same thing as a number multiplied by itself. So that the end result is that the square root of 5 is 5 to the 1/2 power. And this gets to the essence, the idea that these roots, which are these weird square root symbols, and I'll talk more about them in a second, are just fractions. To understand these roots a little bit more, let's just talk for a second about the nth root of something. Because you can have a square root, a cube root, a fourth root, a fifth root. So when we start adding numbers in here, a square root, we don't leave anything, but a cube root can have a 3, a fourth root will have a 4, and so forth. But that's always the same thing as writing something to the 1 over n power. So this is where rational exponents and roots tie back together. Well, a radical expression, as we get into this, is something that has a root in it somewhere. So we're gonna use roots. So we're gonna go back and forth between roots, or rational exponents, and radicals. So we're gonna go back and forth between the two. So let's start with this one. I have this right now in a, and notice I changed it a little bit. This is supposed to be the 2/3 power. So I want to write this in radical form, so as a root. Well, the way I can do that is I can actually go backwards. So all square root properties, all exponent properties go both ways. So if I change this to multiplication, this really, because is everyone okay that 2/3 is 2 times 1/3? Well, I can just put parentheses and break that into x squared raised to the 1/3 power, because this is an exponent rule. We often just go this way, but we can go both ways. Well, based on the last slide, what does the square root, what's something to the 1/3 power mean? Well, it means I'm missing it here. It means that I have the cube root of x squared. All right, so let's try this one. So if I have negative exponents, first thing I'm gonna do is I'm gonna rewrite that as with positive exponents. Next, I can write it as 3 to the 3rd power times the 1/4, which is 3 cubed to the 1/4 power, or is the 4th root of 3 cubed. Now what is 3 cubed? Well, it's 27. So we're using exponent rules, and then all we're doing is then once I have 1 over a number, this number goes here. I often refer to this as to why it's called a root, because roots live under the ground. Well, whatever's under the ground is what root we're using. So let's just do a few more examples. I want you to pause the video and I want you to write this in radical form. Go ahead. Well, hopefully you first recognize I can break it up 7 times 1/11. Break that up even further, and then that's just the 11th root. Now I can't distribute the 7 in because I have a binomial. So I'd have to multiply it out 7 times, and that's going to get ugly, and I don't want to do it with it. So I'm going to leave it like this, and that's perfectly fine. What about this one? Can you go ahead and write this in radical form? Go ahead. Well, hopefully as you did this, you looked at it and said, oh, well, I can do that. First, I can break it up. I can make the fourth root. And you got to this point, hopefully. But you're not done if you got to this point in time. Can use exponent rules to distribute that 3 into here. We can write it as -4 cubed, and then this is going to be 3 times 3 is 9, and then 1 times 3 is 3, and -4 cubed is -64, so that is our final answer. Well, we've done all those examples. What if now we start with a radical and we want to turn it into a rational exponent? Well, the first critical thing here is notice I have a square root. If you go back several slides, what is a square root equal to as a rational exponent? It's something to the 1/2 power. So I can actually write this b cubed to the 1/2 power. Now wait a second. This goes back to what we started this video with. And that means I can multiply those exponents. And so I get b to the 3/2. That's it with its rational exponents. What about this one? Can you write this using rational exponents? Go ahead, pause the video and work through it. Well, a fifth root is something to the 1/5 power. We multiply, so we get 2/5. It's pretty simple going forward. All right, our last example is this one. How could you write this using rational exponents? Go ahead. Well, again, it's an eighth root, which is to the 1/8 power. So we multiply and we get 3/8. So this kind of wraps up this idea about how do we go between rational exponents and radicals. Practice it, get very familiar, and then move on to the next video for the rest of this section.